I'm Mitzenmacher. I'm from Harvard University. I've done a fair bit of work on hashing and hashing-based algorithmics and data structures. So I'm giving some of the introductory type lectures, and today's will be on Bloom filters and such, with maybe a bit of emphasis on the such as we get going. So just to start out, one of the things that I'm going to tend to do in the analysis is, we've already seen Rasmus talk about, and we'll see Mikkel talk about next, this issue of good hash functions, right? And what are we really allowed to assume about our hash functions, and how do things work under certain theoretical models of hash functions? And generally throughout this talk, I'm just going to assume that we have a good hash function. And what I mean by a good hash function is really I'm going to mean a truly random hash function. Okay? And clearly that's a big assumption, but it tends to make the math a lot easier or more streamlined in terms of getting through. And in practice, it actually seems to be a pretty reasonable assumption, and that in many cases, for various reasons, including the fact that you might have randomness in your data, it's not completely unreasonable to treat whatever hash function you have as a random hash function. So we'll just make this assumption as we go through. And the other thing, which is something I sort of keep, unfortunately, rediscovering, usually about halfway through the fact when I'm writing what I think is a new paper, and realize that while it is a new paper, that a bunch of the ideas are the same ideas as several of my other papers, which is that sort of the same themes sort of keep coming up over and over again. So I'll hopefully at times try and make that explicit, but at other times I probably won't. But hopefully you'll get the feeling that some of these things, some of these themes, some of these ideas keep reappearing in various ways over and over again through today's lecture and tomorrow's lecture. All right, so with that introduction being said, let's give sort of the simple couple slide framework of what is a Bloom filter. Okay. And I like talking about Bloom filters for various reasons, but one is just because it's such a simple basic data structure that shows off a lot of key points, I think, about what you can do with hashing. And as Rasmus already started to introduce for us, a Bloom filter is meant to handle a problem that we call approximate membership queries. Okay, so the idea is I have a set, and what I want to be able to do is answer questions of the form, is this new thing that I'm seeing an element of this set? Okay? And hopefully that strikes you as a not particularly difficult problem, right? Even if you haven't seen hashing or hash-based data structures before, you're thinking, well, I could just sort this set of objects, or numbers or whatever they are. I could just sort the darn things and then do some sort of binary search or some other sort of search-based algorithm. I could always just walk through them linearly, even if they're unsorted. There's plenty of ways to answer this question. But this question comes up in a lot of situations where you want the solution both to be fast, particularly faster than doing some sort of linear search or potentially even a binary search through the set of objects. And you want the data structure to be small. That is, you might not actually have enough space to explicitly represent the entire set S. Right? You may have the entire set S represented somewhere, right? But if you're storing this into some small on-chip data structure, you may want it to be significantly smaller than the full representation of the actual set. And as we'll see, because of this, lots of situations where this comes up are in things like network devices, where memory is actually still constrained, or that is to believe in for some people. All right, so because of this fact that we're willing to want high speed and low space, we're willing to tolerate some probability of error. Okay, so the types of probability of error we might have could either be false positives, something's not in the set but we report that it is, or false negatives, something's in the set and we report that it's not. And for a lot of applications, it makes sense to say that we're willing to tolerate some amount of false positives, but we certainly don't want false negatives. So if you think of things like security applications, right? Security applications, if you get a false positive, someone says, wait, you're subject to a security check, even though maybe you shouldn't be, as long as they'll eventually get through, as long as you have some sort of secondary mechanism for them to pass through, things are going to be fine, right? Like when I get searched going through the airport and they, have some sort of false positive on the scanner and feel the need to pat me down or something. It's not wonderful, but it's something I can live with. On the other hand, false negatives in many situations, such as security situations, could be a disaster. All right, so a Bloom filter is just a simple hash-based data structure that allows us to answer these sorts of questions in essentially constant time, or the time it takes to do a hash, small amounts of space. In some sense, the space is independent of the actual size of your objects, whether these are URLs or 128-bit IPv6 addresses or something else. It doesn't really matter what the keys actually are. We're going to end up reducing to a small amount of space. It just depends on the number of items, but with some probability of being wrong. Okay, so that's the trade-off we're going to get. And again, as we start to see an introduction of last talk, here's sort of the basic approach for doing a Bloom filter. This is sort of like my Bloom filters in a single slide, pretty much all you need to know about them. So we'll start with an m-bit array, which will initially be initialized to all zeros. Now, for each of my keys, I'll use that word to refer to the items in the set. Sometimes I'll use elements, or sometimes I'll use keys, or items, or something like that. For each of those keys in the set, I'm going to end up hashing each of them k times. Right? So each one will get hashed k times. I'll have, say, k different hash functions. And when I hash an element, I'll get a location. The hash value I'm going to get, we should think of as a value between 0 and m minus 1, referring to a location in this array. Okay, so for each hash function, for each element, I'm going to get a location, and I'll set that value to be 1. Things may be set to 1 more than one time. That's fine. That just means it's set to 1. So now to check if something is in a set, I'll check my array, my Bloom filter array, by hashing that value k times, right? And I'll check to see if I see 1s in all of those locations. And if I ever see a 0, right, then I know that that can't be an element in my set. Because if I get a 0, if this was an element in the set, all the places should be 1s. So if I ever see a 0, I know that it's not an element in my set. However, I can get false positives if I see all 1s, and it's not an element in the set. Right? It just might happen to hash to locations that other elements have set to 1. Does everyone get the idea of this structure? So I'll have n elements, m equals some constant times n number of bits, okay, and I'll have k hash functions. All right, so for the analysis, okay, we can say, what's the probability a specific bit in the filter is 0? Well, that's just the probability that got missed for each of the n elements and each of the k hash functions for those n elements. Okay, so the probability a specific bit is 0 is 1 minus 1 over m to the kth power, which I'll often approximate with the standard E version of the expression. All right, so now what's the probability of a false positive in the Bloom filter? Well, suppose that after I get done with all this hashing, that I ended up with something that had the fraction of 0 bits being rho. Well, the probability of getting a false positive is the probability that I get a 1 k times. Right? So for something not in my set, what I have to do to get a false positive is I see a 1 k times. Well, the probability I see a 1 any single time is 1 minus rho. If my hash functions are random, the probability I'll see it k times is then going to be 1 minus rho to the kth power. All right, and now I'm going to be thinking in terms of various sorts of approximations. I mean, rho here, rho is going to be whatever the fraction of 0 bits is and whatever I ended up with. But the point is that rho is going to be very, very close to this p prime value. Right? P prime was the probability that a single bit was 0. And by standard sort of concentration arguments, rho is going to be concentrated around its expectation, which is just p prime. And then if I like to write things a bit shorter, I'll note that p prime for reasonable values of m and n is going to be very close to p, the expression where I use the e form of it. Okay? And if I'm using m as a constant times n number of bits, that's just going to equal this form here. All right, and so the reason that these approximations are okay is, again, because rho is going to be concentrated around its expectation. And now if I look at this expression and I say, okay, well, how many hash functions should I use in my Bloom filter? Right? What's the number of hash functions that's best? I can do a little calculus to optimize this expression with respect to k. And I find that k is going to be log of 2 times n over n. And if I plug this back in, this value of k back in, I get that the optimal false positive probability is this constant, which is really like log of 2 or to the m over n. So what does this tell us? It tells us that the more bits per item, right, m over n we can read as the number of bits we're willing to use per item in our array. The more bits per item we use, the Bloom filter false positive probability is going to fall exponentially in that, at a rate of this 0.6185, as long as we're able to pick the optimal number of hash functions. Any questions so far about this? Okay. So I should point out here is that, these approximations that I've talked about, you can, really do a more sophisticated analysis if you want to, right? What we really have is that we have nk hashes into the m buckets. And if we really wanted to find what we might call the exact false positive probability, we could calculate the distribution of the number of empty or non-empty buckets, right? This relates to the Combinatorial royal object known as the Stirling number of the second kind. So then we can get the exact false positive probability, where what I mean there is really what we'd be getting is a distribution over the numbers of zeros and ones in a specific array. And based on that distribution, we could calculate, take the average, the weighted average of the false positive probabilities, depending on the number of 0 and 1 entries in the array. So in general, this would be overkill, except if you're doing very small Bloom filters, right? The asymptotics and the approximations all kick in and all behave very fine for reasonably sized objects. But if in practice you were dealing with, say, for some reason, a very smallish Bloom filter, maybe you'd want to do this just to check that, how far off you were from the analysis in real life. The other thing to think about is, what's going on here roughly? Like, why even is there an optimal number of hash functions? Why isn't just using more hash functions better? Right? So if we think of, or if we try and plot the behavior, we treat the number of hash functions as a continuous random variable. What we see is the false positive probability has a curve that looks like this shape here. This is for the case where m over n equals 8, and the optimal number of hash functions is, roughly, well, between 5 and 6. But if you have to pick an integer, it's going to, just barely be 5. Okay. But so why is it that you wouldn't just say that more hash functions is better? If we think back or go back to this analysis, right? We see k, the number of hash functions, showing up in 2 places. And in some sense, one of those k's is making things better, and one of those k's is making things worse. So maybe just a question to the audience, why is having more hash functions better? That's the other way. That's what makes it worse, right? So
Okay.
the more hash functions I have, the more ones I'm putting in the array, and that's worse, right? That increases the probability of a false positive. Okay, so too many hash functions makes things worse. What makes more hash functions better? Yeah.
Yeah, you have more chances to find a zero.
Right. On the other hand, more hash functions is better, right? Because the more hash functions you have, the more chances you get to actually find a zero. Okay. All right. So what you naturally get from these two behaviors is this trade-off. More hash functions is good. More hash functions is worse. There's a sweet spot in the middle, and that's why you get a plot that looks like this, and where there's an optimal number of hash functions, things get better until things get worse again. All right. So, by the way, a sort of generalization of this trick I used to analyze this, right? At some point I said, the expressions get easier if I sort of take this 1 minus 1 over n to the kn and use the e expression. Okay. You don't really have to, it's just sometimes that helps with the math, and at the very least it makes writing some of the stuff down a lot shorter. Okay. But more generally, that's sort of a signal that there's sort of a useful framework that comes up here when we think in terms of these random hash functions and hashing multiple things. Right, so remember I started out with an array of all zeros, and if I ask the question, how many things hash to each of these locations, right, we know that it's really a binomial distribution. If we looked at any single one, it's a binomial distribution where there are nk things being hashed, and the probability it lands in any specific bin is 1 over n. And this is all well and good and useful in terms of the analysis, but one issue is that these values are not independent, right? You can sort of see they're not independent because in particular at the end of the day, the sum over each of these buckets of the number of things that hashes to them has to equal n times k, right? So they can't be independent. On the other hand, if n and m are sort of going to infinity together, right, so that the average number of things in each bucket is a constant, then as n and m go to infinity, the number of things in each location does converge to a Poisson random variable, okay, with mean nk over m, that can be treated as independent. In fact, it turns out really the only dependency is what I just said before, that the sum of these things is supposed to be equal to n times k. And if we treat these things as independent, right, that's sort of the right framework, the right way of thinking about it. And then you can go back and sort of correct for the fact that these things are supposed to sum up at nk at the end. Right, so what you can make use of is that there are fairly strong theorems regarding this connection between this binomial to Poisson connection for hashing processes. Right, literally conditioned on the Poisson having the right sum, the right number of items, the distribution that you get is binomial. Right, if I say, pretend they're independent Poissons, but condition on this fact, you get exactly the binomial distribution. So making use of that, you can get useful things out, like that Chernoff bounds on various events in the Poisson setting can be applied to the binomial setting as well, usually with just a small factor increase. Okay? So this is a nice way of thinking, and a way of thinking you might want to start as we continue going. When we think about what's going on in these sorts of processes, it's useful to think of independent Poisson and then work out details later. Okay. Right, so sort of the short version of the Bloom filter proof might be, well, the probability a specific bit is 0 is, again, just taking the Poisson random variable being 0 is e to the minus k n over m. If we just sort of take as an idea that things are independent among the bins, then the probability that I get a false positive is just this expression we had before, 1 minus e to the minus k n over m to the kth power. So that's the way that this comes about, by thinking of things as terms of independent Poissons. And again, that's a the right approximation as to what's going on. Taking a note from Rasmus, who I think pointed this out on Stack Machines a while back. So it's maybe even easier to see this if we look at the variant that you can refer to as a split Bloom filter. Okay, so in a split Bloom filter, we say, well, look, we might as well just take our m bits and split them up into k different subtables. So instead of having this one table of m bits that everything hashes into, let's just go ahead and split things up into k subtables of m over k bits. This is a different way of thinking of the Bloom filter. Okay, so now when I do a hash function, I'm just going to pick out one location uniformly at random from each group. Okay. So I don't get these weird situations where two hash functions from the same element could end up landing in the same location. So this turns out to have essentially the same performance. One advantage of this sort of approach in actual hardware is it might be easier to parallelize, right, because you can guarantee that the hash functions aren't going to collide with each other. Again, so in this case, for any specific sort of subfilter, the probability a specific bit is 0 is now going to be 1 over k over m to the nth power, which again is approximately the same value. The one difference is now these k subgroups are themselves, these k subpartitions are themselves truly independent, right? So the false positive probability really is sort of 1 minus b prime to the kth power. And again, we already know the fact that asymptotically these are the same, although in fact, in the split Bloom filter, if I've got my sign right, the bound is actually just, potentially a tiny bit worse, right? Due to the fact that 1 minus k over m to the n is a little less than or equal to 1 minus 1 over m to the kn. So they're asymptotically the same. The split Bloom filter is maybe a tiny bit worse, but it has other advantages, such as it's parallelizable much more easily. Okay, again, any questions so far?
Yeah, why was it worse than the other time?
Because this is the probability a bit is 0, right? And then we're going to take the probability a bit is 1, which is 1 minus that. So the fact that this is a little smaller, the probability that it's a 1 is a little bigger. So the false positive probability is a little bigger. It's because we're taking 1 minus this to get the probability that it's a 1.
But if we split it up, we have, it should only be values that have, for the same hash function that has the same value, right? In one table. We split them up for each
Yes.
hash function.
Yep.
That would give us.
You still have to get a false positive, still has to match on all k. So it's going to be to the kth power. Okay. So I should point out that there are other ways of possibly doing this. Okay. So if we're thinking of a Bloom filter, another possible way to do this, for instance, that's known as to use a perfect hashing based approach. Okay. So perfect hashing says, look, somewhere out there, if you give me the set, you know this set in advance that you want to do this for, I can find you a perfect hash function. That is, I can find a one-to-one mapping of these elements into, n locations into an array. So a different way of doing a Bloom filter, instead of having these storing bits at these random hash locations, to say, okay, I'm going to build a perfect hash table, just the right size. You have n elements of your set. I'll have n locations in this hash table. And in this hash table, I'll store a fingerprint of the corresponding element. I'll do some sort of other hash on the element to get a fingerprint. So then when I'm going to do a lookup, right, of some element, I'll do one hash to tell me where in the array to look things up. I'll do a second hash to get a fingerprint for that element, and then I'll just check whether the fingerprints match or not. If they do, I'll think that that was the element that was placed there. And if not, I'll know it's not an element in the set. It wasn't the element that was placed there. Okay. So one of the things this tells us is for the basic problem of given a set of n elements, find this approximate data structure with a false positive probability of epsilon, right, that Bloom filters are certainly not optimal in terms of the space versus error trade-off, right? So again, I could just get a perfect hash function, one cell per element, and I could store a log base 2 of 1 over epsilon bit fingerprint at each cell. So to test for set membership, hash to find the cell, hash to check its fingerprint, and that gives me a false positive probability of, instead of 0.6185 to the m over n, of 1/2, for each bit, assuming I have, again, random hash functions, 1/2 to the m over n of epsilon. So I can get away with using m is n times log base 2 of 1 over epsilon bits, whereas the Bloom filter ended up using about 40% more space. Okay, if you go back to the number of those values of km and n you have to use, right? Because it's 0.6185 to the m over n instead of 0.5 to the m over n. So there are better solutions potentially, right? But this is has its weaknesses. In particular, it's a less flexible solution, right? The Bloom filter, in Bloom filter, I don't really have to know the exact number of elements in advance. As long as I have a good approximation of it, that's fine. I can always throw in another element in my Bloom filter by hashing that element and placing ones in the appropriate positions. Whereas here, this is a much less flexible solution. I can't readily add new elements without essentially finding a new perfect hash function. The other thing about this that I should say is that in some sense I'm cheating here when I'm saying, right, that the space is only this number of bits, right? There's some amount of space associated with, finding the perfect hash function or storing the representation of that perfect hash function itself. Again, I'm not really throwing that cost in because I was already cheating by assuming that we have, perfect hash functions or, fully random hash functions to begin with. But that's also a cost here as well.
Question?
Yeah.
Aren't you cheating in the Bloom filter as well by not factoring in the space for the hash function?
Yeah. But I sort of said, that's what I just said. And yes, but I said that from day one. But here I'm not only cheating by not counting the face of the quote-unquote perfect hash function, I'm also cheating by not, even if you're using that as a building block, say if we're building your perfect hash function, the perfect hash function may take additional space beyond that. Okay. All right, so given Bloom filters aren't optimal, why would anyone use them to begin with? Yeah.
So is the alternative solution optimal in any sense, or is it?
Yes, it's space optimal. Again, assuming you don't count the cost of the perfect hash function itself. Right? So there's I'll mention, or it's actually left as one of the exercises, sort of a space lower bound. That matches the space lower bound. Okay. All right, so one thing I found, and I've almost found sort of surprising, is again, that's one alternative, and people have come up with other alternatives to Bloom filters, or alternative Bloom filter type constructions that can use sort of the same sort of functionality, but with less space. And so the question is, why would you actually use Bloom filters? Okay? And this is one of the things I try to impart to my students in sort of in my undergraduate algorithms class, is that certainly we can think of there's sort of a trade-off space when we look at algorithms. And the ones that I'd say, well, when I think about undergraduates, hopefully they've figured out that there's a trade-off between time and space. Usually they often just think in terms of time, but you can get them to figure out that space itself is an issue by just giving them big enough problems that quadratic space algorithms start to fail. They'll start to realize that space is an issue. But then sort of another trade-off is correctness, error probability. And this is maybe normal to theoreticians and computer scientists, theoretical computer scientists, and maybe even these days practical computer scientists. But I will point out it's something that, like, when you first get undergraduates and try and tell them, it's like, okay, I'm going to start giving you algorithms that give you the wrong answer. You know, it sort of surprises them and makes them think a bit. But the thing that I'd say theoreticians don't think about in terms of what the fourth trade-off in this space is programmer time, right, is that there are other solutions that can give you the functionality of a Bloom filter, but they're a lot more complicated than the Bloom filter. Right? Bloom filters are easy. Right? So to the extent that the space in the Bloom filter isn't truly the actual bottleneck, or that you just want to get something working and see how it will work, Bloom filters are very popular just because they're so brain-dead simple in terms of their implementation. All right, so let's go through some of the uses of Bloom filters. Right? So the classic use of Bloom filter was back in the days when memory was scarce, which seems like a long, long time ago. People actually wanted to do things like dictionaries in small amounts of space. Okay? And you could use it for spell checking. Another thing you could use it for is something like password checking. You might have a dictionary of bad passwords. You wouldn't want someone to use one of the bad passwords that are easy to crack. And you need these to be small space. You could store them in a dictionary. But you could store that dictionary using a Bloom filter, right? So instead of actually keeping the words in a dictionary, you somehow hash the words in the dictionary, use some sort of Bloom filter, and you can get down to using, if you're willing to accept a false positive rate of about 2%, essentially 1 byte per word in your dictionary, regardless of how long the words in your dictionary actually are. So when space is at a premium, if you think of passwords as being 8-byte strings, you're roughly saving an order of magnitude, a factor of 8, at the exchange of some false positive probability. This is one of the early classical uses of Bloom filters. Sort of another classical use of Bloom filters is actually in databases, where you do sort of a variation of a semi-join called a Bloom join. Right? So the idea of a join in general is you've got two tables that you want to combine. So if we're dealing with a distributed database, one of those tables may lie on one server, and another lie on another server somewhere. And you don't want someone to ship the whole database back to you to join them. So you may just say, okay, I've looked through my side of the database. I need from you any records where, this element is one of these possibilities so that I can do the join. Except that list may itself get long and complicated. Right? So instead of sending that list, what you may actually send is a Bloom filter of that list. The things you need transactions back for. And that would be called a Bloom join. Okay? And so what you might get then is that you might get some false positives, so that the other side of the distributed database may send you back extra records that you didn't actually need. Right? But if the false positive probability is small, that may still be better for you than trying to send the actual list of things that you need, or might need, instead of a Bloom filter. So this was another use of Bloom filters, or the classical use. A more modern use is for large-scale signature detection, right? So for checking for things like worm behavior or other bad behavior in packets, right? So this was sort of the start of deep packet inspection type technologies. So you want things to be very fast when checking through these packets. So you have a list of signatures that you're looking for. So the idea is we'll separate the signatures out by length and build a Bloom filter for the signatures of each length and go through them and check them in parallel. And if we ever see a bad signature, if we ever get a match for any of these Bloom filters, well then there's going to have to be some extra security processing on the packet if we ever see one of those bad signatures. And this is one of these things that seems nice because there's a sort of clear implementation framework in hardware. right? So you've got your analyzer, which is really going to consist of sort of a bunch of Bloom filters that are built up in hardware. And as you're reading in this collection of streaming data, right, you'll be able to easily pull out different length strings, or the last 3 bytes, last 4 bytes, say last W bytes, ship them off to one of these Bloom filters, check if there's a match. And if there's ever a match, you say, okay, I'm going to need to do a bit more work here. Any questions about that? All right, so there are a bunch more applications or variations on these sorts of themes. These days, there seem to be a couple hundred papers a year that are using a Bloom filter in some way or another. Usually for, again, this sort of list processing type work, often in networking algorithms. So there's an old survey that I wrote some time back on network applications of Bloom filters, slightly more modern piece which covers both Bloom filters and other things, but really it's just so hard to keep up, right, that these things are appearing all the time in various sorts of papers, again, particularly for networking applications. And one of the things that I find so unusual is that even though these are out there and so prevalent, they really aren't taught in your, again, your standard undergraduate algorithms course. I mean, they're taught in my undergraduate algorithms course, but that's because I like Bloom filters, right? But they're sort of not part of, the standard CLRS textbook or Kleinberg-Tardos or any of the basic undergrad textbooks. I don't understand why, in the sense that, as we saw, like, you can present them in a slide, right? They're brain dead easy. They're easy to implement, right? They aren't even that hard to analyze. But I think the main reason is that these aren't taught in algorithms. Is sort of historically, when algorithms people think about error probabilities, right? We think about error probabilities that we want to be vanishing, right? We say we want to have vanishing error probabilities. So like, sure, yeah, maybe our algorithm or data structure has errors, but we want to say that you don't really have to worry about that. The probability of errors is small, goes to 0. And to get that would require, essentially log n bits per item if you're dealing with a Bloom filter, which means that you might as well just hash things anyway, right? Just use a big hash string. Don't use a Bloom filter at all. This area where you have sort of a constant number of bits per element and correspondingly a constant false positive probability is actually really useful in practice, right? But it's sort of not useful in theory, right? Because in theory you like to have these vanishing error probabilities. So I think this is why it's not taught in your basic algorithms course, even though it's really such a useful data structure. So before going on to some of the many sorts of variations, right? Sort of the key point here is what you can think of as the Bloom filter principle, is that whenever you have a set or a list of items, and space is any sort of issue, then you should consider the Bloom filter as an alternative. Okay? You think, maybe I want to keep my set or my list as a Bloom filter. Okay? And the downside of this, again, is you're going to have false positives. So you just have to consider what's the effect of false positives going to be on my application. Can I handle a small fraction of false positives? And often the answer turns out to be yes. Okay. Any questions? Yeah.
Yeah, I was wondering, instead of computing k different hash functions, could you just use one hash function that always gives you k bits? Then you.
Well, one function that gives you k bits, or you mean k different locations?
Yeah, like could you construct maybe a hash function?
I mean, that's really like having k
that would
hash
be more
functions,
efficient.
right?
Instead, you could calculate it for one.
I mean, again, that's just, if you model a single hash, right? If you have a single hash, the way to think about it is, yeah, if I have a hash function that gives me 128 bits, and I only need 16 bits to address a location in the array, then it's like having 8 hash functions, right? So in some sense, yes. But it's key that, again, our sort of model is that we're getting, k different independent locations. in a slide. Yeah. Is there another question?
Yeah, it's just, so the bounds are not tight, right? So Bloom filters are definitely not optimal, but we don't know anything that handles everything smoothly and is optimal, right?
We don't know anything.
We don't know something better for these purposes.
No, we do. I mean, I sort of showed you one.
No, because that doesn't handle insertions.
That doesn't what?
Handle insertions, online insertions, right?
Online insertions,
Yeah.
right.
So maybe the take-home message, not to people from the wild, but to other theoreticians, is to find something better, right?
Yeah, and there has been work on that, and I don't know what the best is right now for handling insertions. Although I think I don't know if I reference it here. There are lower bounds that say that if you want to handle insertions, it actually takes more space than, say, the perfect hash function approach. If you want to be able to handle online insertions. And in some sense, if you don't know the size of your set or have some sort of bounds on the set in your advance, they're even worse lower bounds. So there are some people looking at those sorts of variations now, or there have been. Yeah?
Have any compression techniques been applied to, say, usable Bloom filters?
Yes, so I'm actually not going to talk about that, but the paper you want to look at is called Compressed Bloom Filters by someone named Mitzenmacher. So, a question comes up, can you compress Bloom filters? And the answer is sort of yes and no. So if we go back to this value of k to optimize the Bloom filter, what you get when you plug in that value of k and you say, like, what's the probability a specific bit of the filter is 0? If you look up at that top line, you can see the m over n's cancel, and you get e to the minus log 2, which is 1/2. So if you have an optimal Bloom filter and then try and compress it, you're not going to get a lot of compression, because it's going to look essentially like a random bit string. Each bit is going to be 0 or 1 with probability 1/2. On the other hand, if you think of the problem the other way, and you sort of say, I'm going to compress what I get out of my Bloom filter, right? What is the optimal number of hash functions, given that I'm going to compress it? This is no longer the optimal number of hash functions. So you can compress a Bloom filter. It's just in its uncompressed form, it's going to be bigger or sparser. Right? So in its uncompressed form, it's not optimal, but given that you're going to compress it, you can say it's optimal under those circumstances. And so there are things you can do with that, if you're transmitting around compressed Bloom filters. So that's what that paper talks about. But sort of, in some sense, no, in that if you just have an optimal Bloom filter lying around, you can't compress it and make it better.
I mean, I guess it's more or less the same problem, right? I mean, compressing the Bloom filter, you want to then follow the trace a bit down and tell if it's 0 or 1. Right? I mean,
yeah.
So you're back to the original problem.
Okay. So someone just asked about, a way to interpret the question is, gee, these Bloom filters you have sound great, except what if I want to delete things out of them? Right? What happens then? And so, can you just be clear, there is an actual problem here, right? The problem is that multiple things may end up hashing to the same location, right? So I can't just delete things by changing the ones back to zeros again, because it may affect other items, right? If xi and xj sort of share a location, and if I try and delete one of them by setting that value to 0, well, I've actually now deleted both of them in this set, right? So now I'll start getting those false negatives that I wanted to avoid. All right, so one way of dealing this is to keep what's called a counting Bloom filter. Okay? So instead of it being an m-bit array, what we're going to have is really these places we shouldn't think of as bits anymore. We're going to have count keep a count of the number of things that hash there. And then to delete something, I can go ahead and decrement the corresponding locations. And for each counting Bloom filter, or for a counting Bloom filter, I can get the corresponding Bloom filter by just mapping zeros to zeros and anything that's not 0 to a 1. So this would be the Bloom filter, sorry, for this one up here. I just messed this up. Sorry. I don't think this actually matches either of these two exactly. I think I got off when I copied things over. But what should happen is that given a counting Bloom filter, right, just change zeros to keep zeros as zeros and anything that's non-zero, turn back to a 1. All right, so when implementing a counting Bloom filter, one question that comes up if you're concerned about how big your data structure is well, what size are my counters? And here again, we can make use of this sort of Poisson approximation, which tells us that in practice, 4 bits per counter is probably going to be just fine. Right, so you can say the average load, if you have the right number of hash functions, is going to be log 2. So the probability that a counter ever gets up to load 16, right, which would overflow your 4-bit counter, which would be bad, because if you ever have an overflow, then you aren't going to be able to really keep track of the counts, is pretty small. Okay. So depending on your application, you might treat that as an ignorable event, or you may have some sort of fail-safe that says, okay, if that ever happens, I'll flag some sort of emergency and I'll have to do something severe. Okay. But generally what this means is that in a counting Bloom filter, you can get away with just 4 bits a counter. You can also do plenty of other tricky things to do better, right? You could say I'll use like 2 or 3-bit counters, and then if those overflow, I'll put you in some secondary structure, which will tell you what the proper count is. So you can certainly get down to fewer than 4 bits per counter using more complex multi-level schemes. All right, so these counting Bloom filters, I mean, we've now gone from sort of 1-bit objects to 4-bit objects. It's a factor of 4 in space, sort of non-trivial. Might mean that maybe we don't want to be bothering using Bloom filters anyway. Maybe we now actually want to be keeping around these lists of items. In practice, the way these are often used is that you sort of have a counting Bloom filter and a corresponding Bloom filter. Right, so in network devices, this would be typically, you'd say, I'll keep my Bloom filter, which I want to be very, very fast and give me my answers. I'll keep that locally in on-chip memory. Okay? And I'll keep a counting Bloom filter in off-chip memory, which might be slower. Okay. And the idea is that these sort of changes, these updates, where you're going to insert or delete an item, yeah, they're going to happen, but they're going to happen a lot more rarely. Right? They'll happen a lot more infrequently. It's like, sure, maybe I'm going to introduce a new prefix or something into my lookup array structure, but that's not going to happen that often. Most of the time, I'm just going to be doing lookups. Right? So I can do the lookups on chip and keep the extra work off chip. All right, so let me give it sort of another, this is more theoretical, but it's something I have a lot of fun with. Theoretical variations on Bloom filters. One is, get to this point of sort of how you do the hashing, okay, that we've generally been ignoring, which is that instead of having k random hash functions, I can get away with just having 2 random hash functions using double hashing. So double hashing is sort of an old style way of hashing. Says that if I'm going to take a sequence of hash values, if I'm going to try and put something in a hash array, I'll try and hash it. If it doesn't come in its first place, I'll try and put it in a second place. If it doesn't go in the second place, I'll try and put it in the third place, and so on. And this says, well, to pick subsequent places, you really just need 2 hash values. Start with the first, then add in the second, and if that doesn't work, add it again and again and again. Right? So you really have a starting point and an offset. And we can use that to mimic our k hash values. Okay? And it was shown experimentally that this doesn't lead to any difference. And we were able to show this formally, that this actually led to no difference in behavior. Let me give sort of a brief sketch or outline of the proof. It's a bit easier if we look at sort of the split Bloom filter framework. And for even further convenience, I'll assume that the number of bits is, I'm going to have k subtables, each with a prime number of bits, just to make the math a bit easier. All right, so my k hash functions are going to be h1 of x plus I times h2 of x mod p, where I goes from 0 to k minus 1. And gi of x is going to tell me which bit to set in each of these subarrays. So I set the GIX bit of the I subarray. All right, so what are the bad things that can possibly happen here? Okay. Again, so a false positive will happen if what I'm going to get are a number of collisions, right? So let's say that a collision happens. If I'm looking for false positives, I have some element that's not in my set, and it's going to have collisions in each of the subarrays with something which is in the set. That is, it's going to have something it hashes to, where the thing that I'm checking that's going to have the false positive is going to hit some actual element of my set. And the way I've set up this framework, right, with this splitting things up and using prime number of elements in the array, for any pair xy of elements, what could possibly happen in terms of collisions? Well, you can check that the only thing that can happen is, it could be that I don't get any collision at all between two elements. Could be that I get one collision, they hit in one spot. But I can't get that they're ever going to collide in 2 places or 3 places. If they collide in 2 or 3 or more places, it's because they've collided everywhere. And that's easy to check. If they happen to collide in 2 spaces, I and j, right, then just by solving the pair of equations, what I'm going to get is that their hash values must be equal. Right, and if their hash values are equal, they end up colliding in all k locations. So what are the bad things that can happen? Why is that useful to me? Well, one bad thing that can happen, right, is that I could get that this element that's causing a false positive, it's a false positive because it really happens to collide everywhere with some other element in my set. But the key is that's going to be a small probability event. That's going to happen with probability at most n over p squared, where p here is itself theta of n. Right? So it has to do with the number of bits in the subarray. So a bad possible thing that could happen is I get a false positive just because that element looks actually like an element in my set. It hashes to all the same locations. That's a little over one event, and I'm dealing with constant false positive probabilities. That's fine. That's ignorable, or that's vanishing. Okay. So if I ignore that possibility, and I'm sort of being sketchy here, and there's a lot more to this argument, right? Then I'm really sort of back into this world that we had before when we first studied the Bloom filter, right? Where what I'm asking is for this split Bloom filter, right? Is there anything else to check if there's a false positive? I'm saying, well, for each of my locations, is the count bigger than 1? And to figure out the count for each of those individual locations, I can again use this sort of binomial Poisson paradigm to get the false positive probability. Again, it has this same expression. All right, so this is just one of these things that turns out to be kind of nice or useful in practice. So what I've found is these days, if you look at most like online Bloom filter implementations, a lot of people have caught on and are actually implementing things this way, using this double hashing technique, because really it doesn't change the performance in any noticeable way. And to the extent that there's any computation bottlenecks, or this tends to reduce them in terms of computing the actual hash functions. you go on to the next sort of data structure, which extending on this idea of deletions is a count min sketch. And we'll be hearing definitely a lot more about the count min sketch in some of the later lectures, so take this as a very brief introduction to it, but you'll be hearing a lot more. So you can think of it as a variation on this idea of Bloom filters or counts and Bloom filters. Items are now going to have counts associated with them, right? So now I don't just have items that I'm worried about, is it a member of the set or not a member of the set, but an item will have an associated count. This item has shown up 100 times. In routers, you can think of it as, I might think of the number of bytes or packets associated with a flow, right? That would be the sort of thing you'd want to count in a networked environment. And it's going to work essentially the same way. I'll hash the items. Every time I see an item, I'll hash it to k locations. I'll correspondingly increment the count at those locations. And then I'll use as my estimate for an item, or one possible estimate for the item, is the minimum over all the counters. Okay, so here's sort of a pictorial example. We'll generally think count min sketch as sort of a split Bloom filter, just because it makes the analysis slightly easier. You know, some new item, again, maybe it's a flow in a router comes in and has 2 bytes or some other feature associated with it, hashes to a number of locations, and each of those counts has to go up by 2. Does everyone get that framework? All right, and the main idea is that you're not going to get too big of an overestimate by taking the minimum counter as an estimate of the count for objects with a high enough count. So this is going to be good, as we'll see, for handling objects that we call sort of heavy hitters. Right? So you can think of it as, what's the expected amount that goes into a cell? Well, it's whatever the total count is times this k over m factor. Right? That's the sort of, I'm hashing things k times, I have m possible locations they're getting into. So the total amount of weight overall is going to be the total times k, and that's spread over the m cells. All right, so as long as the hash functions are even, as it turns out, just pairwise independent, then for any item x and any corresponding bin b of x that x hashes to, I can say, well, what's the extra at b of x? Well, the estimated extra at b of x is going to be at most, really I shouldn't count x, the amount associated with x in it, but the expected amount extra is at most this total times k over m, okay, t for total. So the probability that the extra is c times that is going to be at most 1 over c, just by Markov's inequality. All right, so because I have k separate hashes, that's going to be the power of the k here. So my estimate, the probability that my estimate of the count is going to be more than this additive ct k over m. It's going to be at most 1 over c to the k power. So for items where my count is big enough that this error term is small, my estimate is going to be pretty good with high probability. Okay, so there's lots of good uses for this, in particular finding the heaviest sorts of flows or objects in a data stream. But there's plenty of other situations where it turns out to be useful for other approximations. And again, I think Graham's going to go over this in one of the later lectures. There's better analysis available for various situations, in particular for skewed data streams. That's like things going to a power law, where counts go according to a power law, which is often a common setting. There's also sort of an improvement to this that's useful in the no deletion setting called conservative update, which I think there's now some analysis and some settings for conservative update, but it's still not fully analyzed particularly well. It's one of these things that works, but is really hard to analyze. Okay, so an item y comes in, and we say, okay, it's got to be incremented by 2. Okay? And we know that we're going to be using the minimum as sort of our estimate for that value. Well, looking at that, we can say, well, wait, y is certainly at most 5. Sorry, yeah, at most 5, right? Because if y was bigger than 5 after this increment, then all of the counters should be above 5, but the minimum counter is going to be 5. So if I know that the count associated with y should really be at most 5, why should I take this counter that's 8 and add 2 to it and up it to 10? That doesn't gain me anything. It just makes things more inaccurate, right? It adds waste that might affect other things that are hashing there. So I can conservatively update by essentially saying, oh, okay, take the min value, add in the corresponding increment, and make sure that everything's above that, right? But that's all I have to do. So the 3 will become a 5. The 4, I could increment it to 6, but that's wasteful. That doesn't gain me anything. I can just set it up to 5. And this 8, well, there's no reason to change it at all. It's already bigger than the biggest value y could possibly be. So by doing that, I can reduce the total amount of sort of waste, the amount of extra that I'm adding into the system, which means that I should get better estimates. And you actually do get much better estimates, usually this way. Unfortunately, trying to analyze how much better those estimates are turns out to be a very thorny theoretical problem. Again, except in, I think, some special cases, conservative update hasn't really been analyzed. Yeah.
Does this depend on the order of insertion?
Yes. Once you do conservative update, what you actually get will depend on the order. Yes.
But it's impossible to find the optimal ordering.
Well, so generally, I think when you think in terms of analysis, you don't necessarily get to choose the ordering. Maybe you could assume it comes in a random ordering, if that would help the analysis. But I don't think even in that setting it's known how to balance.
But you lose the deletions.
What?
You lose the deletions.
Yeah. You also lose the ability to
Some sense,
delete.
very much
Right?
like
This
the
is
original
no longer
Bloom.
reversible.
Yeah.
Right? So if you just increment and you wanted to delete something, then you could decrement it, like a counting Bloom filter. Right? Once you do conservative update, you lose the ability to delete. That's for the other feature. Okay, so I'm going to introduce sort of another variation of a Bloom filter, or a Bloom filter-like structure, to solve a problem that's called the stragglers problem. Okay, so again, in thinking in terms of network devices, you can think of the problem of flows that don't terminate, right? So I'm maybe keeping track of flows going through my network, some that don't terminate, so at the end of the day, I'm going to have a collection of these bad leftover flows. I might want to list them out. Or if we want to think of sort of a simpler example in terms of building security, maybe you could imagine keeping track of all the people who are entering the building on a given day, right? And then people leave during the day, and at the end of the day, you want to just check that everyone who's entered has left, and if there are people who are still left over, you want to know who the stragglers are. But in particular, what's challenging, or what our aim is going to be here, again, you can imagine that this is easy to do just by keeping a list, right? This is the way things typically work in building security. You have to sign in, and then you come back and sign out. Okay. So as a data structure, that doesn't feel like it's a particularly compelling solution, in that the size of that list you have to keep is the size of the number of people that have entered and leave the building. That's a potentially very big list. What you'd like to do is have something that's proportional to the size of the people left over at the end of the day, right? That's the only time that you really care about actually producing that list, explicating that list, right? So keeping a list of everyone that's come in during the day is very wasteful in terms of space. Right? If 1,000 people come and leave the building during the day, but there's only like half a dozen stragglers, right? You've just kept this very long list for a very small output solution. So the question is, can you come up with something that's proportional to the size, again, at this sort of end of the day, right, at this time when I want to list the numbers as opposed to generally? So a related problem, right, is this notion of a set reconciliation problem, right? So this is sort of the database version of the problem, right? Alice and Bob each hold a set of keys with a very large overlap. So we could think of this as a distributed database problem where you have sort of copies of the database, but they're loosely synchronized. So some keys get added to one database, some keys get added to the other database, maybe some get deleted as well. You want to sync up the databases at the end of the day. You want to do that without trading the actual databases, right? The databases may be very big. The delta between the databases, if they're loosely synchronized, should be very small. All right, so can both sides learn what the set difference is, learn what they need to update, but again, proportional to the size of the difference, not the size of the actual sets themselves. All right, so you could do this just with Bloom filters. Alice and Bob are going to trade Bloom filters of their sets. Alice can check her elements, determine, which are not in Bob's filter, and vice versa, and they can each send those. The problem is there might be false positives, right? Alice may look in Bob's filter, say, oh, does Bob have this element? And get a false positive, say, oh, Bob has this element even though he doesn't. Right? So what you're going to have to do is do things over a number of rounds. Right? So this will get you most of the way. Right? This will correct you most of the way, but you may have to do additional rounds to correct further for false positives. Okay. But also the other negative part of this is that even with this simple Bloom filter scheme, the transmissions we're talking about are now still, they're smaller. They'll be using Bloom filters. You're not trading around the actual databases, but you're still sending around something that's proportional to that size. Right? Not to the actual set difference itself. So if you happen to have a large number of differences, maybe this is a good thing to do, but if you think you have a small number of set differences, maybe it's not the right thing to do. So I'm going to talk about a sort of different structure. We'll call it an invertible Bloom lookup table, or sometimes called an invertible Bloom filter, which allows you to insert things, delete things, but also list the entries. But the point is that the list entries will only succeed as long as there's a small number of things actually in the system. So I can insert lots of things, have a lot more than I could possibly have for listing. I could then delete them, and then at the end of the day I'll be able to list as long as the number of things left in the table is sufficiently small. All right, and this is called an invertible Bloom lookup table or invertible Bloom filter, precisely because unlike regular Bloom filters, right? Regular Bloom filters, you've hashed stuff in, you're just left with a bit string of zeros and ones. You can't pull out what was actually put in. But here, this is going to be invertible. We are going to be able to pull out what was put in as long as it's small enough. So there are variations of what you have to store depending on your need, but let's go ahead and talk about invertible Bloom filters. Each cell is going to hold a count of the number of things that have hashed there. A key sum, which will be sort of a sum of the keys, where by summing I mean taking an XOR. And also keep track of a checksum. That is, I'll hash each item using some sort of checksum hash, and I'll keep a running sum of those checks as well, right? Again, by using XORs. What I'm going to end up doing at the end of the day, after all the various insertion deletions, is look for locations in here where the key sum and the checksum match and the count equals 1. Right? That is, I've actually found things which seem to have just one item in them. And moreover, that assuming that there really is one item in there, the hashes match. And I'm going to assume at the moment that my checksum is enough that I'm never going to pull something out that doesn't actually correspond to a single item. Right? That I'm not going to have any failures, that the checksum will catch me from trying to peel something out that doesn't correspond to a single item. All right, so what this looks like, for example, is like this, where I say, okay, I've got a bunch of things. Oh, I found something with a count of 1. Okay, and the other places it hashes to are these other locations. I found something with a hash of count of 1, and I'll assume that the hash matches the checksum. So I can peel it out. I can actually pull the key out, right? Because there's just one item in there, so this key sum is going to actually equal the key. I'll pull it out, and once I delete it, that will update the count for these other locations. And in particular, it might give me a new location, which just has one item in it, which I can then pull out and keep going. Okay, and the hope, or the way you have to set up this data structure is so that you can peel everything out at the end of the day. Okay, so how do we solve this set reconciliation? Alice and Bob create their own invertible Bloom lookup table. Okay. They trade them. Alice deletes her items from Bob's invertible Bloom lookup table. Notice that you could actually get things that have a count of 1 when you're doing this sort of inserting and deleting that aren't really a single key left in the cell, right? Maybe Alice inserts 2 things into a cell. Bob deletes one other thing that isn't either of those 2 things, right? So you could get a count of 1 even though there are 3 items associated with that cell. That's why we have the checksums. But as long as they go through and peel to these recover items, there's a theorem that says that the space required is only order the size of the set difference. And in fact, it's a small constant factor, generally around the number of cells you need is roughly easily made to be within a factor of 2 of the set difference. But notice that we're also keeping a checksum as well as the original hash values in account. So the total space is maybe about 4 times the size of the set difference. But you can actually peel everything out using the right sort of data structure this way. So you get something that's fully invertible, again, as long as things are small. I think we're getting close to the end, but a couple of other just quick things that you can do with Bloom filters. Okay. You can use Bloom filters, for instance, to get a good estimate of the similarity of 2 sets. So you can think of the Bloom filter as a sketch of the set. Okay. And you can say, okay, I'll take these 2 sketches and I'll take the dot product. Okay. So whenever 2 sets have an item in common, there's going to be a 1 in several locations that are the same, right? The locations that that item hashes to. So in some sense, the number of locations where they both have a 1 should give you a measure of how similar the 2 sets are. Okay. So by finding the dot product, you can estimate the intersection or union of 2 sets. And there's actually an exercise on that, which I'll hand out towards the end. In particular, the exercise is to sort of prove the following formula, which is if I take the intersection, what's the probability that a bit is set? It's 1 minus 1 over m, k hash functions times the size of the first set, same thing, size of the second set, plus the size of this union. Okay, so if I know the sizes of the 2 sets, I can find the size, or estimate the size of their union, and hence their intersection. Okay, so Bloom filters is a way of estimating, but I'm going to point out some recent work that was done by myself and Rasmus and Nim, wave up there, which is a better similarity sketch in the case when you think the similarity is going to be high. And it's based on, I think you'll see some of the other ideas we've seen throughout here. Okay. So instead of keeping counts within a cell or trying to do anything tricky like that, what we'll do is just keep the parity of the number of elements hashed there. Okay. We call this the odd sketch. It's just keeping track of the parity of the count, whether it's even or odd. Okay. So if I'm taking sort of the joint two sets, that's one plus, or the exclusive OR of two sets, right? So I mean that things that are in one set, but not in both sets. Okay. The odd sketch for that is going to be exactly the exclusive OR of the corresponding odd sketches. Okay. All right, so to figure out how many ones are in an odd sketch, okay, or in particular when I'm taking two sets and putting them together, I can use a Poisson approximation. Okay, so again, elements that are in both sets are going to cancel each other. So what I'm going to find is I'm taking really the odd sketch of the number of elements in there, sort of the set difference, the things that are in one but not the other. Okay. So the probability that it is going to be 1 is going to be approximately the probability of the Poisson random variable with mean n over m. Right? I'm just going to be hashing things once here in the odd sketch, not k times. So if I have n objects, that gives me n hashes. And if I have m cells, that's m bits. The mean number of times it's going to be set or hit with a 1 is n over m. So I'm asking what's the probability of Poisson random variable with this mean is odd, which you can calculate takes this value. Okay. Which again is going to be one of the exercises. And so given the number of 1 bits, and given that I know what m is, I can estimate n, the size of the set difference, from the number of the 1 bits. These have been tested and work out very well on natural high similarity problems, such as testing for web duplicate detection and in the area of association rule learning. And this was a recent paper that just appeared in www. So I'll have like a bibliography of stuff at the end, and this is just something recent, sort of showing that, again, we're still finding more uses for these sorts of hash-based sketches, which use these sorts of ideas. We had some talk about dynamic Bloom filters, right? So we want to allow the addition of items, but suppose we want to allow, keep allowing the additions of items. You know, so the way to think of this problem is at each stage I might be adding new items in, but at every stage I want to have at most m bits, and I want to have a bound on the false positive probability. Okay? So there's been some recent work that shows that, again, if you have this Bloom filter and you want this ability to add items in, right, that you actually do require more space than what was required for, say, the perfect hashing approach, or sort of the minimal approach. So this was something that wasn't known for a while, whether you could actually do dynamic Bloom filters and get the same sort of space bounds, and now it's been answered negatively. And there are even stronger lower bounds, as I said, when the number of items that you actually want to store isn't even known in advance. So there's been some other recent work, and then this I'm just sort of ending up with some highlights of recent work. The odd sketch was recent work. This dynamic Bloom filters is recent work in the last couple of years. Sliding Bloom filters. So suppose you have a data stream going by you, and you want to keep a Bloom filter type data structure over the last n items in the stream. So it turns out a useful generalization of this is to say, to give yourself a little bit of wiggle room, to say that, okay, for the last n items in the stream, you want to be, you don't want to be able to answer yes, right? You don't want any false negatives. Between the nth item and the n plus mth item, you're sort of allowed to give any sort of answer, right? But once things age enough, once you get to items of age n over m, n plus m, then the false positive probability should be epsilon, just like for any other item, right? So once you're sufficiently aged out of the system, you truly are forgotten. If you're new, you should be answered just like you're a Bloom filter, and sort of in between you have a little bit of wiggle room. So there's been some recent results that say that constant epsilon can be done in space, n log n over m plus order n. One question I have, I've sort of seen the paper, and I can't tell from the paper, because I haven't tried to implement it, whether their proposed scheme is really practical or not. It'd be interesting to sort of test if it was useful for real type of applications. Okay, it's clearly getting close to time for lunch. To conclude, again, we have this Bloom filter idea, which is really based on this idea of using multiple hash functions, right? The multiple hash functions gives you the standard sort of exponential decrease in the false positive probability. But more importantly, also, this other idea of just using multiple hash functions. It's a very simple way, simple framework for building a data structure. Okay. And because of that, we see just innumerable variations, some of which are useful, some of which may be less so. But it's clearly, I've just presented, some of the very, very many variations, and certainly not all of the useful ones. Okay, so this is a very powerful paradigm that still, I think, has room to grow. There are definitely ways that you can imagine doing things better, but again, there's an interesting trade-off between doing things better theoretically and actually being useful in practice. That often requires non-trivial, careful thought about what the applications are that you're thinking of. So we've had this idea, and in the next lecture that I'll be giving tomorrow, we'll be continuing on this theme of multiple hashing, but looking at a different sort of framework. So in what we call the balanced allocation framework, talking about the load distributions you can get when you use multiple choice hashing. And also for cuckoo hashing, which is a novel type of hashing data structure that keeps high memory utilization and low load by using multiple choices. I do have some exercises, and there are copies down here of the corresponding slides, and the slides will be up. The way I would think about these exercises, they're not like all part of the same family, and for those of you who feel that you need to do something to show that you've done something while here, as Mitchell said, to get a diploma, I would say, like, I'm an easy grader. You should think about doing one of these exercises, maybe. Pick what you think is the easiest or most favorite one. One of them, as I said, was just, you can imagine taking the dot product of Bloom filters to do size estimates. One is deriving this fact that for a Poisson random variable, the probability that it takes on an odd value is given by this expression. One is to prove sort of lower bound, so that if you have a big universe, that you really do need something like n log over 2, 1 over epsilon bits in order to get a false positive probability of at most epsilon to represent sets of size n. One was this idea that for the counting Bloom filter, recall that I said that you could sort of use a secondary structure. That if you had overflow, you could somehow say use one of the values to represent that you've reached your limit, and then use some sort of secondary structure, which should hopefully be smaller, to deal with those rare cases. So if you want to try and design a slightly more efficient counting Bloom filter using fewer bits per element, that would be a good exercise. And this one's a bit more open, but if you want to think about it, a common problem is that when we talk about Bloom filters, we talk about false positive probability. And the idea of a false positive probability is that you're saying, suppose I pick some element not in my set, what's the chance that it gives a false positive probability? In actual applications, it may be that you're getting the same item multiple times hammering the Bloom filter, right? So you could imagine that there's, if you're keeping a Bloom filter of bad IP addresses, right? And there's some false positive, so there's a good IP address, but it's being marked as bad and having to go through all sorts of security because of that. Right. Then eventually that IP address may get fed up and say, can't you do something about this? Can you correct the fact that I seem to be giving you false positives all the time because I'm coming in 100 times a day? Right, so while your false positive probability on your Bloom filter may be one thing, the false positive rate, that is the rate of false positives you see, depends on your actual inputs. Right? Depends on what you're looking up in the Bloom filter. Okay. So the question is, can you have Bloom filters adapt in some easier, natural way? What's a design that you would think of to deal with trying to lower the false positive rate once you've actually seen something about the inputs? So those are just some possible exercises. Again, they'll be down here, and I would say you could think about them at your leisure. And again, just doing one of them would be just fine. My point of view. Okay, that's it for me.